Thank
very
you,
much.
sir.
Right. Thank you. Yeah, please tell
Good
me.
Thank you
night,
very much,
sir.
sir.
Good
Yeah,
night,
right.
sir.
Good night.
Good
Good
night.
night.
Thank you.
Thank you, sir.
So, can we have a
Participant,
break?
yes, yes. So next session will start from 8 o'clock. Okay, so I think 15 minutes. So after 15 minutes, the next session will be taken by Dr. and Professor Halder, Sumanta
Sumanta
Halder
Halder.
from IIT Bhubaneswar. So see you at 8 o'clock.
So, you can stop the recording.
Okay.
Then you'll restart again.
So welcome back to the next session, which will be taken by Professor Sumanta Halder. So before starting this session, let me introduce about him. So firstly, let me just tell you it's because I did my PhD from IIT Bhubaneswar, so I was already having anything, I mean, quite familiar about this, sir. So let me start. It is my privilege to introduce the esteemed speaker, Professor Sumanta Halder. So Professor Sumanta Halder is a professor civil engineering and head of School of Infrastructure at IIT Bhubaneswar, distinguished expert in geotechnical engineering. He earned his PhD from ISC Bangalore and specializing in soil structure interaction and the risk reliability-based design of pile foundation. His doctoral research earned him the Professor Leonardo's Best PhD Thesis Award from Indian Geotechnical Society. With over 15 years of academic and research experience, Professor Haldar's expertise spans offshore geotechnics, high-speed railway infrastructure, and soil structure interaction with a focus of renewable energy and infrastructure, particularly offshore and turbine foundation. His research emphasizes the combining mechanics, mathematics, experimental studies, and the computational modeling to develop the innovation solution to complex geotechnical problem. Professor Halder has published extensively in high impact factor journals, conferences, addressing both theoretical and advancement of practical challenges in geotechnical engineering. His contribution includes developing the advanced model for geotechnical systems applying reliability concept for enhanced safety and assessing the seismic performance of offshore structures. In addition to the research, he is deeply involved in teaching and mentoring, having the guided numerous masters and doctoral students. Beyond the academia, he collaborated with the industry, government organization on critical projects such as Offshore Foundation, Pile Raft Foundation, and Railway Geotechnics. Addressing Indian unique geotechnical challenges, Professor Halder is also an active contributor to the Global Geotechnical Committee, organizing workshops, delivering invited talk, and serving the leadership roles within this professional society. May I now invite Professor Sumanta Halder to begin the session. Over to you, sir.
Yeah, so Dr. Krishna, thank you for your introduction.
Thank you, sir.
I will share my slide. Am I audible to all?
Yes, sir. Yes, sir. You are audible.
Okay. So this is a late evening time. It's not a good time to
Yes,
discuss
And
critical
I'm
things.
sorry, sir. Actually, you asked me for some other slot, but
No, it's
I
fine.
was
I'm just just joking.
okay, sir. Thank you,
Yes,
sir.
because the participants are also waiting. So how much time I can take?
Till
Up-
9:30.
Okay. Okay, fine. So is my slide visible?
Yes, sir.
Okay. All right.
Make it slideshow, sir.
Yeah. So can I turn off my video, or is it required?
Sir, your compatibility.
Huh?
Yes,
Okay.
sir. I
Yeah.
mean, if internet is not up to the mark, so you may switch off your video, sir.
Yeah, that will be better. I hope this is visible now. I just make it, yeah. So now is it a full screen mode?
Yes, sir. Yes, sir.
Okay, so a very good evening to all, and thank you for this opportunity. So basically, I'll be talking on design of offshore wind turbines for India's sustainable growth. So basically, the sustainability, so this particular faculty development program, it's mainly focusing on sustainability and resilient infrastructure that I can see in the title. So I will talk about, so I have many slides. So let me see, so how many slides I can cover. See, the sustainability part, I hope in the first session it is discussed to some extent. So I'd like to just mention about the sustainability. The sustainability, if you look at this diagram, it's a very interesting diagram. It's a basically composition of social, environment, and economic of and these three basically it should be harmonious coexistence. And whenever we talk about sustainability of any project, we need to look at it. So all the harmony of among all these components. Quickly, we'll see the sustainability and geotechnology, how geotechnology is included, that geotechnical infrastructure. So how the sustainability can be achieved and why the sustainability is important. So nowadays, if you can see that construction industry, the 40% of the global energy consumption, it's mainly due to these construction activities around the world. And not only that, it depletes basically the conventional materials like the natural materials, sand, gravel, and stones, and it is basically a big challenge in nowadays in construction industry. Because the problems of climate change, ozone depletion, and other important aspects that we are nowadays talking about, these are all related to this consumption of the natural resources. And nowadays, we are basically looking at the alternative option. Uh, for example, the use of waste material and other aspects. So that may reduce the consumption of the natural material. So in my lecture, I'll just touch upon all those concepts like how the sustainability is. Initially, I'll talk about the sustainability part, then how the several components are there in sustainability in a particular project. We can manage this by considering certain things. And out of all these methods, I'll just talk about the energy foundations and all, how this will be a sustainable development. In terms of sustainable development, this will be a meaningful step. So in a sustainability, so if you look at the sustainability aspects, the sustainability of a system is, it's a basically definition of the sustainability. It's a ability to survive and retain its functionality over time. So it's a very important concept. Nowadays, we are all talking about sustainability. So the basics of sustainability of an engineered system, it mainly dependent on these four concepts like efficient, reliable, resilient, and adaptive. So these are the four important components of sustainability. For any project, we need to look at all these components. So efficiency means the efficient use of resources, the natural resources or environmental and its environmental impacts primarily. And we know the reliability of any project, it's very important. So we need to look at basically the reliability of any design or the use of any sustainable material. So we need to look at the reliability of that. So overall, it should be sufficiently far away from its predictable failure states. So all the structures are basically designed based on the failure criteria. So we need to apply sufficient factor of safety or other aspects so that it should be away from the failure. And the resilient is a very important term. So it's a bounce back. So basically when the system or the structure is disrupted, so how quickly it can be functional within acceptable period of time. So that is called the resilient infrastructure. Nowadays, resilient infrastructure is very important aspects in terms of sustainability. And adaptiveness, that is also important because it basically deals with the it should be adaptive. That means in terms of the see, suppose we if we are considering the change in the infrastructure due to certain disrupts or certain load conditions, so it should be adaptive. That means it should have natural changes within itself and its environment, and it should have a flexibility of the modification at any point of time. So moving to the next slide. So the objectives are well defined. If you look at the objective is very simple, like an engineering system, and it should be natural and man-made environment without compromising its functionality. So that is important. And not only that, when we're talking about the sustainability, so this dynamic, so basically it's a dynamics of 4 E's. If you look at this diagram, its diagram is very interesting. So it's basically it's all combination of environment, economy, engineering, design, and equity. So these 4 aspects should be satisfied. So that means 4 E's. It's a dynamic harmony of dynamic interaction among all these components. So that is what we are basically talking about, the sustainable goal. Now, in a sustainable project, so basically when we are talking about sustainability, so we should look at the sustainability objectives, which need to be incorporated for a particular project. See, what we have observed, that in several construction or several infrastructural project, many things are not planned. So all the stakeholders should be involved at the planning stage itself, not after the construction or during the construction. So at the initial stage, we need to, all the stakeholders should have a interaction among all the stakeholders, and some sufficient planning should be there. So because sometimes some decisions taken which may not be altered during the construction time, so when we have been called, so that is a big challenge nowadays. So this aspect should be satisfied during all projects. And not only that, reliable, resilient design, already I have mentioned this, and it should be designed in such a manner so minimal financial burden should be there. And whenever we are using certain material, so we need to look at all those aspects. So minimal use of resources is another important aspect. So in terms of planning, design, construction, maintenance of geotechnical facilities, we need to look at those utilization of those material. So maybe some waste material may not be locally available, so you need to procure. So you need to plan accordingly. So which material is available at nearby site, so that you can minimize the cost of transportation and other aspects. And not only that, the existing geotechnical failure. So definitely the reuse of the geotechnical facilities, that may also reduce the financial burden and the possibility of minimizing the waste. So normally in a construction industry, we produce a lot of waste, and this can be minimized. So if you look at the sustainability aspect in a project, so multi-criteria based assessment framework is well defined. So in general, we in a geotechnical design, say life cycle assessment, cost benefit analysis, environmental impact assessment. So these are all important aspects of any sustainable design. And resource efficiency is basically, this can be assessed using some sustainability index. Like you can give certain score for a particular project in different components, like resource efficiency score, environmental impact score, and socioeconomic impact score. So these are all important aspects of sustainability. So for any project, you can define that. These are all important aspects of sustainable assessment. Now, coming to the sustainability aspect, so in my discussion, I will mostly talk about, see, in a geotechnical project, various aspects are there, by which you can achieve the sustainability. Like, say, use of waste material is one of them, and the use of energy, suppose some energy foundations, the concept of energy foundations. So for renewable energy converter foundations, then optimization of the geosynthetic material. So many aspects are there. So out of all the aspects, I will mainly focus on the energy foundations aspects, which can definitely address the sustainable challenges, sustainable goal in terms of India's growth, future growth. So global, if you look at the global primary energy consumption, why we are talking about the energy consumption? Because nowadays we are talking about the renewable energy. So renewable energy has a lot of challenge in India. So in next couple of decades, we will look into those aspects. So the renewable energy development is growing very fast in India. So if you look at the energy demand, so India's energy consumption is increased it will be increased substantially from 5% to 11%, more than double by 2040. So to achieve this, you definitely, we cannot only rely on the fossil fuels. And so definitely we need to look at the alternative arrangement like green energy. So the target shares of renewable energy in India power consumption, you can see these figures. So over the decades, you can see how it is improving. So this particular percentage, that solar and non-solar, because nowadays our Indian government is mostly looking at the solar energy. And now slowly we are moving towards the wind energy. Of course, wind farms are already there in India. Those are all onshore wind farms. So I will talk about some offshore wind farm development and how these aspects can be taken forward in near future. So you have to take it forward. So definitely we need to see certain aspects of renewable energy development in India. So looking at those aspects, like definitely we have a lot of scope for the further development. So if you look at this diagram, state-wise renewable energy potential in India, you can see this is mostly different. It's basically renewable energy potential in terms of solar and wind. If you look at this pie chart, the Rajasthan and Gujarat and Maharashtra, these are the major contributor to the renewable energy potential in India. So, and thereafter Karnataka and other states. So you might have seen in Rajasthan, a lot of wind farms are there. In Gujarat and Maharashtra and Karnataka. So I think a lot of solar power and as well as the wind energy foundations wind energy structures are installed. So not only in these states, definitely some other states are also having a lot of scope. So slowly we are moving towards that. So considering this, so I will just briefly talk about the solar energy and how the geotechnical engineers can contribute to the solar energy infrastructure. So if you look at the National Solar Mission by MNRE, Ministry of New and Renewable Energy, they have supported a lot to development for the development of solar energy in India. And solar energy projects, a lot of you must have seen a lot of development happened in solar energy. So by 20 gigawatt by the year of 2021, and it will become more than 100 gigawatt by the year of 2022. Of course, this is the old data. And see, basically, but as it was expected, it may not have been implemented till date. So Made in India initiative promoted by Government of India has a lot of it's a very important initiative. So basically that supported the solar installation capacity in India. Now currently, if you look at the position of India, it's the fifth highest solar install capacity worldwide. And if you look at the solar infrastructure, mostly we think about the solar rooftop. But if you look at the ground mounted solar infrastructure, so we have a lot of solar power plants in Rajasthan and Gujarat area. So those are all ground mounted solar panels. So those solar infrastructure has a lot of scope in terms of geotechnical aspects, mostly the foundation aspects, and of course the superstructure design. So there are the two different types of solar infrastructure, low mounted and elevated ground mounted solar panel system, where the foundations are most important aspects, because any solar panel is designed based on the wind speed. And if it is in a seismically active areas, we need to look at the seismic ground motion as well, because these solar panels are very sensitive. So sensitive to deformation that may damage if any excessive deformation of the solar panel may cause the deformation in the infrastructure, and that may damage the panels. So therefore, any any kind of installation, that the foundation should be sufficiently strong enough. And not only that, some other important aspects of the solar foundations are it should be easy to install and it can be done very quickly in a particular site. There are a lot of scope in terms of geotechnical engineers, essentially for foundation engineering aspects. Like we can have typical solar ground mounted solar panel foundations like drill pier, then backfill precusper and backfill pedestal. So these are all different type of foundation, shallow foundation, deep foundations, both are available. And relatively new, and you can see that screw pile concept is nowadays coming up. And the screw pile is a very interesting foundation type which can be easily used for the solar installation, because these helical piles or the screw piles are basically, it's a steel tubular pile. It's made of steel and with a helical plate, and it can be easily installed at any ground within no time. And those helical piles, see here in this picture you can see one, in the schematic you can see one helix, but in this diagram in the picture you can see multiple helix. So here we can have 3 helix. So this helical foundations of the screw pile foundation can be easily installed by using a torque. So this is a torque producing machine. So you need to you need some installation torque. The installation is very fast. It can be done very quickly. So the designing of the screw pile is very much challenging, essentially for solar installation, because see the solar panels are subjected to wind. So of course the wind which hits the solar panel, that may create a lateral force to the foundation as well as uplift other than vertical force. So uplift force and lateral force, it's very important for the design of such foundations. The helical pile play a major role in terms of, say, helix. Those helix will give a lot of pull-out resistance than that of the straight shaft piles. So in general, in almost all the locations, the foundations are mostly the concrete piles, the precast concrete piles or cast in situ concrete piles. Those are all straight shaft piles. But the helical piles are becoming very popular, and because a lot of research have been done on this particular foundation. In fact, in our laboratory also, we did a lot of study on helical pile. So the helical pile, the major challenge to improve the lateral capacity. So it's basically in conventional practice, the helical piles are mostly designed in terms of pull-out. So it has a greater pull-out resistance, but at the same time, we can look at the improving the lateral capacity. So lateral as well as uplift. So those combined capacity can be improved. There's a lot of scope of research related to helical pile when it is subjected to different type of loads. Now, coming to the wind energy. So if you look at the wind energy concept, it is basically the India has a lot of wind potential, as we know. So amounted around 35 gigawatt, but it has achieved, but as a target of 60 gigawatt by 2022. But still the wind power has not taken that up to that height. So basically it is progressing. So there is a worldwide installed capacity of the wind power. You can see that by 2022 it has been installed. So in India, if you look at the Indian aspect, so we have a lot of scope, like in terms of wind power, that I will show you. The offshore wind energy in India is very much challenging, and I will tell you about the current scenario of the offshore wind, because in offshore, the wind resources are very high. That means you can expect large wind speed than that of the onshore condition. So therefore, you can have this. Just a moment. Yeah. So the offshore wind energy, if you look at the this particular diagram, so in 2015 there is an agreement at United Nations. It's called Paris Agreement. And it has been decided that by the end of century, we need to achieve 1.5 degree pathway, 1.5 degree centigrade pathway. That means by the end of this century, the global warming should not reach beyond that. So that means it should not be more than 1.5 degree centigrade temperature rise. Now, to achieve this, we need to install more renewable energy. And if you look at in terms of wind energy, offshore wind energy, so we need to install a lot more. So you can see that by 2050, we need to install at least 2000 gigawatt capacity over the entire world. Now, as per the current scenario, the government of India has announced the National Offshore Wind Energy Policy in 2015, long back. Now, according to the World Bank, if you look at the potential, the 112 gigawatt bottom fixed and 83 gigawatt floating offshore wind potential is already there, with the best opportunities in Tamil Nadu and Gujarat. And as per the current scenario, the cabinet approves the VGA funding to install around 1 gigawatt offshore wind, 500 megawatt each at offshore coast of Gujarat and Tamil Nadu. So this is the current status. And now the work is going on in this area, in these two areas, and the installation will be very soon, it will be implemented. And that will produce renewable energy electricity about 3.72 billion units annually, and annual reduction that will, of course, it will reduce the 2.98 million tons of carbon dioxide. And that will be an equivalent emission for a period of 25 years. So it's a huge development in terms of sustainability goal. So just I will talk about a little bit of just a moment. It's not, I think it got stuck somewhere. Is it? Okay. Now it is moving. Yeah.
Hello, Krishna.
No, it's now
It's
moving.
working. It's working.
So if you look at the wind turbine capacity, I will just briefly mention about the wind turbine capacity. So if you look at 2004, the rated power, that means how much electricity it can produce. One wind turbine can produce around 5 megawatt. So in the 2004, you can see the wind energy potential, say in one wind turbine can produce around 5 megawatt. But if you look at the current scenario, nowadays around 15 megawatt or 20 megawatt wind turbine is also available. So one wind turbine can produce a huge amount of energy, like as high as 15 megawatt. And of course, we are developing. So by year of 2028 or 2030, you'll get around 20 megawatt and beyond. So it has enormous capacity. So India has very long coastline, 7,600 kilometer, and it is having very high potential of offshore wind. So Gujarat and Tamil Nadu, they have around 70 gigawatt potential of offshore wind turbine. And definitely it will not only meet the 50% of energy requirement from India can meet that by 2070. And that will, of course, will go by net zero by 2070. That is a goal. 2070 should have zero emission, carbon emission. So this is the typical offshore wind farm. You can see it's a wind farm. It has lot many installations, a lot many wind turbines. So these are offshore wind turbines, offshore wind farm. So let me just take you to some concept of wind turbine. Okay, so I hope you have got a fair idea of the wind turbine mechanism. So it's a very complex mechanism. So at any wind speed, it can go up to maximum 59% efficiency. So it cannot, any theoretical capacity cannot. So theoretically, you cannot go, or practically you cannot go beyond 59%. So it is difficult to achieve that percentage also. So the why the wind turbine is important. We are discussing about the wind turbine wind energy. So basically, we as a geotechnical engineer, we look at the foundation aspect as well as the soil structure interaction aspect. So it's a very interesting topic of research, and you can see the cost breakdowns of the offshore wind farm over water depth is very, very large. Like as the water depth is increasing, so a 10-meter water depth means it's a seawater depth. It is 10 to 20 meter. the cost of foundation is 19%, whereas if the water depth increases to 40 meter to 50 meter, the cost will be around 36%. So you can see as the water depth increases, the cost will be of course the cost will have enormous increase in terms of foundation design, foundation installation, as well as the foundation cost. So the design of foundation is very important, optimum design of foundation. So if you look at the offshore India, just quickly, I'll go through the offshore India. So this is a typical offshore India map. So western offshore, eastern offshore. And these are all basically the offshore platforms where those are installed, like Bombay High, Krishna Godavari Delta, Mahanadi Basin, Hooghly Delta, and Park Strait. So these are all different locations where the offshore installations have been done. Not the wind energy foundation, but the typical offshore oil rigs or offshore platform. So this is a typical continental shelf of India. Continental shelf is basically the land below the sea, and it is within the 200 meter from the shore, from the coast. The west coast has an enormous continental shelf, that means 200 kilometer, at least 200 kilometer away. So the continental shelf extends up to 200 kilometer, whereas the east coast has 30 kilometer in Madras and 40 kilometer at Vizag. So relatively deeper water is very so in eastern side of the India, you'll find the water depth will come very early. Exactly after 30 kilometer or 40 kilometer, the water depth increases substantially. So depending upon the water depth and the soil condition, the typical foundation design should be made. So this is a typical eastern and western offshore soil condition. In Hooghly Delta, mostly you'll find the sand silt mixture, and then Mahanadi Basin, it's mostly clay. And Godavari Krishna Delta will also have the clay sediments, and in Bombay High, mostly it is a mixture of calcareous deposits of clay and sand. So calcareous deposits are mostly the shell fragments and other material. So if you, in summary, if you look at the soils in Indian offshore, the carbonate content will be more in western coast and western coast soils than the eastern coast soils, and normally consolidated clays mostly find in west coast of offshore. And in east coast, you will find very soft clay like under consolidated clay or NC clay. And the soil profile is very complex at various locations. So you can see the soil, a lot of variations in uncertainty in soil in eastern and western offshore. So this is a typical map of offshore soil, different type of soils. And 200-meter water depth contour is basically the boundary between shallow water and deep water. So deep water basically you can see up to 2000 meter or 2 kilometer water depth contour. So definitely at different water depth we can expect different types of foundation. So need for soil investigation is very much important, as we know. So water depths, currents, wave state, temperature gradient, hazards, stratigraphy, all these are very important components for foundation design. Now, if you look at the foundation design issues, mostly it primarily it depends on it's related to bearing capacity of the subsoil, then permanent displacement of the foundation, because it ultimately leads to the settlement of the interstructure as well as the tilting of the structure. So those are all important aspects. Cyclic displacement is another aspect, important aspect, because any foundation, any structure which is installed in offshore environment, it is subjected to wave and as well as wind. So the waves are acting over the entire life of the foundation, so which are cyclic in nature. So definitely over the long run, over the long duration of loading, we need to see the displacement, the accumulated displacement of the foundation. Apart from that, various other aspects like all the piles, mostly driven piles in offshore environment. So pile drivability is important aspect of the foundation design. So when the piles are being installed, the drivability study is very much important. So sometimes it may lead to the damage of the pile if the drivability analysis is not done correctly. Then during the driving operation, pile got stuck. Sometimes you can find excessive amount of pile deformation. So sometimes we may lose the pile. So because offshore installation is very expensive, so any kind of the design, mistake in design may lead to enormous damage in the foundation in terms of cost, in terms of course, the material aspect. So these are all important aspects of the foundation design. Definitely the seabed also may be prone to liquefaction at the seismically active areas. So these are all also very new state of analysis, like liquefaction potential analysis at the offshore environment. It's also important. Apart from that, scour and erosion is also important, essentially due to the wave-induced scour. So the required parameters, just have summarized some certain parameters. You can look at quickly those parameters, because I will just highlight certain important aspects of the foundation designs in various areas. So these are all important aspects of the design and the design issues and the corresponding parameters, which need to be determined either based on the field observation, in situ testing, and the laboratory testing. So coming to the offshore wind turbine foundation, so this particular diagram will give you a brief idea of different type of foundation. As you can see, water depth up to 30 meter. The different type of foundations like gravity-based foundation, suctioncation, monopile. So these are all different names of the foundation. So it's a gravity-based foundation, suctioncation, monopiles. It's a single tubular pile. Then tripod foundation. It is having 3 legs. Jacket foundations, mostly at intermediate water depth. But when the water depth goes beyond 60 meter, these type of foundations are called bottom fixed foundation. Bottom fixed foundations are grounded. That means these are all installed at the seabed. But those foundation system may not be optimum when we go beyond 60 meter water depth. So under these circumstances, floating foundations are important. So otherwise, this foundation installation, bottom fixed foundation installation will be extremely difficult, may not be feasible option. So beyond 60 meter water depth, mostly we'll go for floating system. So I'll discuss mostly on fixed bottom foundation and floating foundation for offshore wind turbine system. So if you look at the summary, so the grounded system or fixed bottom system, it has different type of support structure: monopile, jacket, tripile, tripod, gravity based. And in floating system, it's a very typical type of foundations are available, like tension leg platforms or TLPs, semi-submersible, and spar buoy. Just look at the different type of foundation pictures. So the first one, it is a gravity based foundation, which is having a very large structure at the bottom, so which will be stabilized based on the gravity of the foundation. And this is a suctioncation foundation. It's a jacket with a suction bucket. Suction bucket is a typical type of foundation. It is just like a bucket, and when it is placed just on the seabed, due to the suction, the foundation will be pushed to the seabed. And this is a typical monopile foundation, so which is a single tubular structure, and it is unlike the regular pile foundation. Like the regular pile foundation, mostly we handle within 3 meter, maximum 1 meter, 2 meter, or 2.5 meter. But monopile foundation, essentially for offshore wind turbine foundations, are very large. So more than 3 meter, 4 meter, sometimes you can go for 8 meter. So you can imagine how big is the structure. So this is a typical tripod foundation. The installation of the tripod foundation will be done at the seabed location using this floating barge. And these are the typical floating system. You can see different type of floating system. The first one is a spar buoy system. This is a floater. And this is also a semi-submersible kind of foundation. This is the name of the foundation. These are the floating pontoons. 3 floating pontoons are there, or sometimes we even use 4 floating pontoons. And these are tension leg platforms. This is also a floating pontoon, but the entire system is fixed with a ground anchor system with a tension, because these all the anchors, these are called the mooring lines. Moorings are under tension, so that's why it is called tension leg platform. So these are the typical foundation concepts. So nowadays, these semi-submersible type of foundations are mostly installed in various locations. Like in Japan, they are looking for the semi-submersible type of foundations, which are mostly it can be designed with more stability than that of the spar buoy foundation. Now, these are the gravity-based foundations, a quick look, and these are the tripods. So out of all the bottom fixed foundation, monopile is the most preferred one. You can see that. So based on this pie chart, you can see the monopile foundations are mostly preferred because of its easy installation and it's very simple structure. Floating systems, floating platforms are mostly adopted when the water depth is more than 60 meters. Even it can be installed at 200-meter depth also. So I'll just keep this video. It's basically a installation video of a.
The potential for clean electricity. The crane lifts the monopile into place before driving it deep into the seabed. A transition piece is placed on top of the monopile. It will provide a solid base for the turbine and serves as platform for technicians arriving by boat. With the foundations in place, the ship returns to port to pick up the wind turbine components. State-of-the-art installation vessels can load 4 complete 8-megawatt class wind turbines. That's 4 towers, 12 rotor blades, and 4 nacelles, which have been pre-assembled on land to reduce time spent at sea. Under ideal conditions, it will take just 24 hours to load all 4 turbines onto the ship. Specially designed fixtures and sea fastenings ensure they arrive safely at the site. Lifting yoke with automatic connections. The generator and all the other electric install the nacelle safely in less than 2 hours. Now it's time for the 3 rotor blades. These giants measure 81 meters long each, or roughly the same size as the wingspan of an Airbus A380, the world's largest passenger jet. As the enormous blade draws level with the nacelle, the technicians make the last adjustments. The blade docks smoothly and safely. With technicians working almost exclusively at the Beaufort scale, in weeks, technicians connect the cables and thoroughly test all the turbines in the wind power plant. Once the power plant goes into operation, the wind turbines feed into a single offshore substation.
Okay, so this is an typical installation procedure for monopile foundation. We can have the pile group also, but these are not very much used for offshore installation because of the installation difficulties. Mostly we go for these monopile foundations for various offshore installation at shallow water depth. So just I quickly go through different type of foundations again. So this is a typical type of foundations. So we can have different type of arrangements. So these are all different arrangements of the foundations. And the floating offshore, I'll talk about the floating offshore later on. So let me just quickly go through so this is a typical semi-submersible foundation which is installed at Fukushima, Japan. It's installed by high wind installation. All right. So now coming to the power generation capacity of the wind turbine. So you look at this diagram. So it's a very interesting diagram. So at different wind speed, it can generate different level of electricity or power production. So at a particular speed, it achieves its highest capacity. So suppose a wind turbine is having 5 megawatt capacity. So it can achieve its maximum capacity, or it's called rated power. So rated output power, say suppose if it is 5 megawatt capacity or 10 megawatt capacity, it can attain at a particular wind speed. And cutout wind speed, so this is called rated wind speed. And at a very high wind speed, it may damage the wind turbine blades. So it has its own inbuilt mechanism for the shutdown mechanism. It's called the shutdown mechanism. So cutout wind speed is basically that wind speed beyond which it cannot produce the electricity. Basically, it will stop the wind turbine power production at that speed. So if the wind speed goes beyond the cutoff wind speed, so wind turbine basically it has a self shutdown mechanism. just to protect the wind farms, because those turbine, if it gets damaged, the replacement cost is very high. So this is a typical component of a wind turbine. So if you look at this structure, so there's a substructure. It is basically it is called the monopile foundation, so bottom fixed foundation, and in between tower and the foundation, one component which is called the transition piece. The transition piece, it has a boat landing mechanism and the ladder and the platform just for the maintenance purpose. Boat lands here, and any kind of maintenance work can be done through this transition piece. And the top part is basically the generator, power generator. It's called the nacelle, and the blade, it has a 3-bladed wind turbine. We call it as rotor nacelle assembly. So RNA. It's called RNA assembly. Now, coming to the future trends, if you look at the wind turbine capacity and the rotor diameter, so it is a very large wind turbine. So like 20 megawatt wind turbine, the one rotor diameter could be 250 meters. So it's a huge wind turbine. So you can just compare with the Boeing 747. So it's the largest aircraft. If we consider a 2.3 megawatt wind turbine, so it is the wingspan. So if the rotor diameter, it's as big as one Boeing 747 aircraft. And if we go for a more higher capacity, 8 megawatt or even 15 megawatt wind turbine, you can see how big is the wind turbine. So this is a typical dimension of 15 megawatt Siemens Gamesa wind turbine. So the height of is called the hub height, is called 150 meter, and the rotor radius, that means one blade span, is 120 meter. So it's a huge structure. And the seabed, we call it mudline. So the monopile embedment length most typically varies from 30 meter to 50 meter. And transition piece dimension is around 15 meter. So this is a typical height. It may also vary. So feasibility of bottom fixed wind turbine, if you look at the Indian scenario, so the feasibility of bottom fixed wind turbine at different locations of the offshore India, it has a very promising like wind resource availability, and if it is more than 6 meter per second, and within the water depth of 5 to 200 meter. And depending on various other factors like proximity with the existing port and the transmission grid availability. So because grid connectivity is another important aspect. So in terms of in Indian aspect, you can see the primary foundation types are identified as monopile and jacket. And floating wind turbines also have a lot of potential alternative in deep water. Now look at the offshore wind development. So this is a typical the wind map near Gujarat and Tamil Nadu. These are the two important locations where the government of India is looking for the offshore wind energy development. It has a very high wind energy potential. That's why these two locations are initially chosen. And these are the locations where the wind installation is going to happen. So these are the blocks which will be used for the development of those offshore wind farms. This is at the west coast of India near Gujarat, and another location is near Tamil Nadu. Now, coming to the design of such system, it has a lot of challenges. Like in western coast, essentially in Gujarat region, it's a high seismic zone. At the same time, it is also prone to cyclonic risk. So we need to have a multi-hazard risk assessment at these locations. But in Tamil Nadu location, it's seismic. It's not very seismically active, but it may also have the high wind speed and cyclonic activities. So different location has different type of risk or multi-hazard risk assessment that need to be done. Now coming to the feasibility of the floating offshore, when the feasibility maps are developed, so we need to look at various aspects like wind resources, bathymetry, then ports and logistics, then transmission grid availability, then seismicity. So all these components are basically considered, and we give certain weightage like 40% to 7.5% depending upon the cyclonic map, seismicity of the particular location. So we can develop the feasibility or the feasibility map near some particular location. So some initial development you have done. So this is a typical tentative map of the floating offshore, where the floating offshore is possible. So it's it's a preliminary analysis that we have got. And if you look at the shallow and deep water conditions, because floating offshores are installed in deep water, so this is the typical location of the typical contour of shallow water and deep water. So within this yellow marking, the water depth will be within around 100 meter, and beyond this yellow marking, the water depth is beyond 100 meter. So that's why this particular zone will be considered as deep water, and within this zone it is shallow water. So at different water depth, we can have these two different type of foundation system. So if you look at the feasible locations of different type of wind installation, so fixed offshore wind turbines are feasible within the 50-meter boundary, so 50-meter water depth, and beyond 50-meter, these are the possible locations of floating offshore. And these are the typical soil profile at those locations. And this is near Tamil Nadu area, so where the fixed wind turbines are within this zone. The problem in Indian coast near Tamil Nadu is the deep water is approaching very rapidly. Like you have seen that in the previously, that within 40 kilometer, so the continental shelf will end within 40 kilometer or 30 kilometer. So that means deep water will approach first. That is very much different from the western coast. So the floating offshore can be developed, but we need to have a little bit. We need to have little bit attention regarding the drastic change in water depth at the Tamil Nadu region. And if you look at the seismicity at these locations, then Gujarat is very much seismically active, and in some location it is very high, like zone 5. It comes under zone 5. And some areas are also potentially liquefiable zone. So we need to look at all those aspects. These are the typical fault lines nearby those feasible locations. So definitely we need to look at the seismicity also, and the entire system, the behavior of the entire system or the response of the system due to the seismic activity need to be looked at. And Tamil Nadu region is less active in terms of seismicity. So now just I will talk about little bit about the wind turbine design. So these are the typical loads. So there are two different loads are acting. One is the wind load and the wave load. So just as a layman's term, so when the wind turbine is rotating, it has a certain speed. So these are all very low speed wind turbine. So rotational speed of the wind turbine is very less. So mostly it can be around 0.2 hertz or 0.3 hertz, like that. So when it is rotating, it can have some centrifugal force. The centrifugal force will create a kind of imbalancing force. That force is defined as 1P. And when the wind turbine blades are rotating, it is giving some shadowing effect to the tower, because when the wind blades are covering the tower, so the wind thrust will be reduced when it is covering. So that will happen 3 times in a complete revolution. So that's why the tower will have the frequency of 3 times of the operational frequency of the wind turbine. So because it's a 3-bladed wind turbine, so those are called the 3P loading, 3P frequency. So we can have this centrifugal force acting on the wind turbine. We can have the wind thrust. Also, we can have the wave loading. So these are the important loads acting on the offshore wind turbine. So this is a typical overview of the 3P loading concept. So when the tower blade is just simply coming just in front of the tower, so wind thrust will be reduced by some amount. And again, when the blade just passes through the tower, and when it is crossed, the wind thrust will be increased again. So the typical the time history of the different type of loads you can see from this diagram. So 1P load It's a typical centrifugal force due to the operational frequency. And this is a 3P load. It is 3 times of the operational frequency, which is acting on the tower, and the wave load. Wave load is considered to be cyclic in nature. Now, design approach, a very interesting design approach is available, which are called the soft design, soft tip design, and steep tip design. So 1P frequency, these are basically the rotational speed of the wind turbine. It is not a fixed operational frequency. It can operate within a range, maybe some 0.2 hertz to 0.1 hertz to 0.2 hertz. Maybe there is a rotational speed. So these are called variable wind speed, variable speed wind turbine. So 3P is 3 times of the 1P. It is the range of the frequency. So when the natural frequency of the wind turbine is within this 1P and 3P, we call it a soft steep design. And when the natural frequency is below 1P and 3P, less than 1P and 3P, we call it soft design. And when the natural frequency of the wind turbine is above 1P and 3P or greater than 1P 3P frequency, we call it the steep design. So what are the implications of this 3 design system? So look at this diagram. Soft design will lead to very slender structure, and soft steep design to some extent is relatively intermediate kind of structure, but steep design will be very heavy structure, which is not economically viable. So mostly we follow the soft steep design. So when the rotational frequency and the 3P frequency, the natural frequency will be within that band, 1P and 3P. So I'll just keep this slide for the time being. These are the foundation modeling aspects. You can see the overall structural system can be modeled by different system, maybe fixed base model, which is a very crude approach, or maybe the soil structure interaction part is ignored here, and coupled spring model and Winkler spring model. So this is more relatively like you can say that it is a more rigorous approach. Maybe, of course, the 3-dimensional system will be more rigorous, but you can we can consider this Winkler spring based approach as well for the foundation modeling and the overall structure. This is a typical beam and spring based model, like beam on elastic foundation based model for the foundation system for the design of a monopile foundation. So the PY spring approach, these are all basically due to the lateral load, and TZ springs are due to the vertical load. So both the springs are attached to the pile or the beam element to model the interaction behavior. Now API, so basically American Petroleum Institute, they have certain guidelines to develop those PY curves. So that means these are the interaction curves to model the lateral behavior of the pile. And that means pile soil interaction can be modeled using those lateral soil springs. So load deflection behavior of these springs will follow the PY spring, so which is developed by API, that means American Petroleum Institute. But the PY curve that mostly we use for the design of monopile foundations, it has certain limitations also that I will discuss about the limitations. So the foundation soil interaction is a typical foundation soil interaction, because here mostly the foundations will be subjected to 10 to the power 7 to 10 to the power 8 cycles of loading, some millions of cycles of loading because of the wave loading. For the entire design life, it can experience millions of cycles of loading. So surrounding soil will be subjected to continuous cyclic loading. So we need to look at the soil behavior, the nearby the foundation, due to this long-term cyclic loading. So for clay, for sand, the behavior will be entirely different. So those aspects need to be studied. Just I will skip this slide. So development of the PY curve for the lateral loaded pile, these are the conventional approach of the development of the PY curve. Many of you know about this. And for lateral loaded pile, these are the typical PY curves. The concept of PY curve is very simple. It's nothing but the change of stiffness due to different level of deformation. It's a nonlinear interaction with soil and pile. But the limitations of PY curve, so basically for monopile foundations, the PY curves are mostly developed based on ultimate limit state approach, that ultimate capacity. But the monopiles for offshore wind turbines are mostly guided by serviceability limit state, where the code suggests some very less amount of tilting of the foundation. Tilting of the foundation is allowed up to 0.5 degree at the mud line or at the ocean bed. So this is a very stringent criteria, but ultimate limit state is very like the offshore foundations, like the monopile foundation, mostly is designed based on serviceability limit state, unless it is exposed to extreme loading. So ultimate limit state is basically checked due to the extreme loading condition. But in mostly in an operational condition, we look at the serviceability limit state approach. So therefore, the PY curves has certain limitations. PY curve is not accounted for the long-term cyclic loading. So mostly the PY curves are developed based on the conventional piles, which are limited to around 1 meter or 2 meter diameter. But monopile foundations are mostly having a very large diameter piles, like 3 meter, 4 meter. So the PY curves, so it needs further development of the PY curve for large diameter piles. So these are the typical limitations. So this is a typical PY curve. So this is an interaction curve we mostly use for clay and sand. And this particular diagram, this particular curve is for cyclic loading. So these are the PY curves stipulated by American Petroleum Institute, which are mostly used for monopile design, but it has certain limitations as well. These are another type of typical PY curves which are further developed for which is basically related to the number of load cycles. These are another set of curves for different type of load cycles. Now, importance of soil structure interaction is very much required. So basically, you can see this diagram. So this study has been done. So if you look at the response, so if I consider the soil structure interaction, and if we ignore the soil structure interaction, so you can see there's a substantial variation of responses in terms of rotation, displacement, and bending moment. So this particular study we have conducted initially when we started working on this particular foundation system. And the typical long-term behavior, there is a lack of data available. So like the monitored data from the site, because there is no data available from the site essentially for the wind turbine foundations, because it is subjected to millions of cycles of loading. So due to lack of information, so normally we go for laboratory investigation. And also some data sets are also like it's a confidential data. So normally you may not get those data or information from various industry. So some studies, some laboratory-based studies have also conducted. So it's a basically scaled model test. So if we conduct this long duration test at basically scale down, so we have done some tests on the monopile foundation by actuator. And in case of model test, the similitude relationships are very important. I'm not going into the detail of this similitude relationship. It is very simple. Like when the real structure and there is a prototype structure and the model structure. So it should be it should have some similitude relationship. Otherwise, the model test what we are conducting that may not be upscaled for prototype structure. So therefore, we need to follow certain similitude relationship. That means mass of the tower and the foundation and the superstructure of the prototype structure and model structure should have similar kind of ratios. Now, if you look at this experimental result, you will see the natural frequency of the system, it is reduced substantially. So from 18 hertz to 16 hertz. Due to the large number of loads. So we have limited to 50,000 number of cycles. So the natural frequency of the system, it's reduced. At the same time, you can see the damping of the system is also increasing a little bit over the number of cycles. So another important aspect also, the nearby soil also, the change of stiffness of the nearby soil is also important over the number of cycles. That basically essentially increases the rotation of the monopile, or in terms of the response of the system, that will also increase over the number of cycles. So why this is important? Because we need to satisfy certain design limits. So the limit state of serviceability need to be considered in this case. Now coming to the seismic design. So as you have seen, essentially for Gujarat region, it is highly seismic zone. So what are the important aspects of seismic design, essentially for this kind of structure? So what happens really generally during the seismic motion, if the acceleration at the top, that means it's an acceleration level or the RNM level, or at the hub level, if it increases, so basically it can activate the emergency shutdown condition. So it has some limiting value of acceleration value at the hub height. So if it exceeds because of the amplification of the motion, so definitely it will activate emergency shutdown condition that may reduce the electricity production. That may be the implication in terms of the energy loss and the power production loss. So that's why the design of such system should be done in such a manner so those conditions can be avoided. And typically, in general, the building structures are designed based on the horizontal earthquake motions. But in case of wind turbine structure, the vertical components are also important. Now, if you look at the other scenarios, like seismic liquefaction is also one of the important aspect for this kind of foundation. So just I will go through one more important aspect of this. So basically you can see the tilt of the entire system over the number of cycle is very important. So this is very much important. So over the design life, it should be within the limiting tilt, right? So in case of seismic load, if it is subjected to liquefaction, the foundation may have a substantial amount of tilt that should be avoided. So this is a typical world map where the wind installation is going to happen, and these are the typical locations for the wind turbine installation location, and these are the high seismicity areas. Now I'll just go into the important aspects of the vibration, like the modes of vibration. If you look at the modes of vibration, if the foundation length is reduced, that may activate the rocking mode of vibration. So you can see the difference in the vibration mode. So as the foundation length is decreasing, the foundation modes are also altering. So from sway bending mode, so basically the bending mode is prevalent here, but if the foundation length is decreasing in trend, the rocking mode will be activated. So that means the short piles with liquefaction will have more tendency towards the rocking mode of vibration, so which may result in more tilting of the foundation, which may be detrimental for the design. So these aspects are very important. At the same time, these are the important modes of vibration for the jacket structure. So for the jacket structure having shorter pile length, the rocking mode of vibration is more dominant. So those aspects need to be seen. The vertical modes of vibration is also important. For the short pile, with liquefaction, you can see the natural frequency will be close to the predominant frequency of the earthquake. So latest study we have conducted is, you can see the vertical mode of vibration when we consider the seismic motion and its predominant frequency in the vertical direction. So essentially we are looking at the vertical component of the seismic motion. So when it is very close to the natural frequency of the system, the amplification is very high in these cases. You can see that. Similarly, the liquefiable soil, you can see the natural frequency, how natural frequency changes at the operational phase. It's slowly increasing because of the densification of the sand, but liquefaction phase, drastic reduction in the natural frequency. And when the liquefaction occurred, so thereafter what will happen, when the earthquake stops due to the post liquefaction behavior, that means when the pore pressure will be released, after that again the densification will take place, the stiffness will increase slowly, so again it will gain its natural frequency. So this is a typical behavior of the natural frequency, how the natural frequency changes at different stages of the wind turbine at different, say, at the operational phase, liquefaction phase, and the post-liquefaction phase. And some prediction of the permanent tilt of the monopile in liquefiable soil, those studies have been done. So developed certain cyclic response diagram, which will be useful to predict the damage assessment of the monopile supported wind turbine in liquefiable soils. So more details are available. So those who are interested, they can see all those papers which are published. Now, coming to the bottom fixed wind turbine, essentially for jacket structure, just I will quickly go through it. So you can see for certain structure at this level, as I was mentioning, the amplification is less, whereas for other structure, amplification is very high. It depends on the natural frequency of the structure, the frequency content of the earthquake motion. For certain earthquake, you may have a very large amount of amplification at this level. And if this acceleration goes beyond certain limit, it may activate the emergency shutdown condition that may reduce the electricity production. So the importance of the vertical motion is important. The risk assessment is also studied in certain cases. I will not go into the detail of that. So if you look at the different foundations, if you see the comparison for the monopile and the jacket supported structure, if you look at in terms of the seismic vulnerability, just look at this diagram. At different earthquake loading, the jacket supported structures are less vulnerable in terms of seismic damage condition. So if you look at the if we are looking at the foundation, different type of foundation. So if we compare with monopile and the jacket structures are less vulnerable in terms of the damage criteria. In terms of damage criteria, because it is widely spreaded foundation, it is more stable. So therefore, those kind of assessment should be done for a particular site before we commission this kind of system. So these are the typical codes. DNV codes are basically from Denmark. IEC is European codes. GL code is from Germany, and DNV GL is again a DNV and GL. It's a combination of the German code and the Denmark code. So where all these codal provisions, they stipulated certain guidelines in terms of seismic design criteria, and some codes suggest multiple earthquake loading. So that means when the earthquake happens, we can have two components or three components mostly, the two horizontal component and one vertical component. So both components can be considered for the design of such system. A recent study done by us, you can see that. So if I consider the bidirectional component of the motion, you can see that at differences when the structure is installed, the earthquake can come from any direction. So if the angle of attack varies from 0 to 360 degree, how the response of the system changes. You can see substantial variation is observed at different angle of attack of the earthquake. So therefore, multidirectional earthquake need to be considered for the design. So in summary, I'd like to highlight a couple of things like API-based POI curve. Already I have mentioned that it cannot predict the long-term responses. So you need to you have to make more precaution when we are using these API-based POI curves for the prediction of the responses. At the same time, the fundamental frequency of the system, the determination of the fundamental frequency at different loading condition need to be assessed. And definitely the responses of the system will be governed by the amplitude of the load and need to be assessed with repeated load cycles. Now coming to the very quickly, I will just go through the offshore wind turbine structure in deep water and design strategies. Just I have a couple of slides left. So these are the three different systems like the mooring stabilized TLP and spar and semi-submersible type of foundation, where the geotechnical engineers have role in terms of anchor design. And of course, you can also look at the overall response of the system. And of course, the seabed liquefaction is one of the important aspect. Like if one anchor is lodged due to the seismic liquefaction, that may disturb the stability of the entire system. So if you look at the earthquake hazard assessment for these three type of system, we have various other important aspects. Like ground shaking is one important thing, where liquefaction, vertical shaking, these are the important aspect, where the anchor can lose its capacity. At the same time, the fault movement, like if the anchors are installed near the fault, so the fault movement again, that may increase the settlement of the anchor. So those aspects need to be studied essentially for the floating offshore structure. So these are the design challenges for the fixed bottom and floating offshore wind turbine. So I'll just quickly just discuss of the numerical model. So how do you model those structures? So you can see this is a typical spar floating wind turbine. So it has a different modes of vibration. So it can vibrate in the vertical direction. It can rotate about both the horizontal axis. So each component has different names. So we have the heaving motion, that is the vertical vibration, yawing motion, that is the torsional mode of vibration, and roll and pitch are mostly the rotation with respect to the horizontal axis. Similarly, the surge and sway, these are the lateral vibration in both horizontal axis. So this type of structures, the essentially the design and the modeling part is very much challenging. So when we model such kind of structure, we need to consider the buoyancy and similarly the resistance offered by the water when it is vibrating. So it's a very complex part of the analysis. Essentially, we did it using Abacus or any other software. So if you look at the seismic vulnerability aspect of different type of structure, essentially the floating structure, the spar, semi-submersible and TLPs, these are the relative comparison. So overall, you can see the TLPs are most vulnerable because of the structure itself. As I have already mentioned, TLPs are basically connected with the pre-tensioned mooring lines. So that's why the seismic waves can easily pass through those tendons. Whereas the spar and semi-submersible type of foundations are connected with a mooring line, which are basically it is basically a kind of flexible system. So the seismic waves cannot easily pass through these cables or the mooring lines. So that's why these are all less vulnerable in seismically active areas. So those studies have been done using simple Abacus modeling. And if you look at the comparison between the floating offshore and the bottom fixed wind turbine, so at different water depth, you can see the jacket structures are more vulnerable than the floating offshore wind turbines. So this can be a important outcome in terms of the seismic, in terms of the design of such system in floating system and the fixed bottom system. So in a highly seismically active areas, the floating system can be a good option for those to avoid the seismic damage of certain system. So at the conclusion, just I would like to highlight that some of the important aspects that we have already discussed, that the multidirectional seismic loading is important. At the same time, the floating offshore foundations are basically seismically less vulnerable than the fixed bottom structure. So these aspects need to be considered for the design. And also you can see we have seen that jacket structures are more susceptible to seismic shaking than tension leg platform. And mostly these aspects are important, as already I have mentioned already. So long-term operational viability, if you look at the long-term operational viability with respect to the fixed bottom design, this can be a game changer. So with this, I would like to conclude here. So I want to acknowledge my doctoral scholars who have been working in this particular domain, and some of the MTech scholars are also involved in this part. So this, thank you for the attention.
Thank you very much, sir. The
Thank
session
you.
was really interesting, and not only by enriching this but also practical. I would request to the participant to apply this learning in their academic and research results. And I truly admire that your depth of knowledge, especially in turbine, the clarity which you explain complex concept. So now this is open for the questions. Before that, there are some question in the chat box. Let me just
No,
read
let
it.
them
Read.
ask. If any of the participants have any confusion or doubt, you please switch on your unmute your video microphone and then ask. Was there anyone?
Yes,
Good
sir.
evening,
One.
sir.
Okay.
Yes.
Hello.
Yes, you
Yes,
are
yes.
audible.
Sir, good evening, sir. I have a doubt regarding the soil structure interaction numerical modeling, sir.
Okay.
So usually when we are modeling, we consider the base as the fixed base. I mean, the soil below we consider it as a fixed. So how to model the surrounding boundaries, sir? Should we consider it as an more a free field condition, or should we bind something in the end condition, sir?
I'll show you. Is my slide visible?
Yes,
Yes,
sir.
sir.
Yes, sir. Yes.
I think I have covered this part. So if you look at the foundation modeling aspect, which you are uh, looking at, so these are the typical fixed base model, so base at
Yes,
fixity at
yes, sir.
base. And
Yes,
this is
sir.
a typical soil structure interaction model, which I
Yes,
have
sir.
already discussed. So basically it can be modeled as a Winkler spring.
Yes,
So
sir.
this particular structure can be idealized as a beam,
Yes,
and
sir.
those lateral springs can be modeled. So I think I have shown another important diagram. So look at this model.
Yes, sir.
So see, these are called the lateral springs. And to model the vertical interaction, you can also incorporate these vertical springs.
Okay.
PY, TZ spring, if you are aware of these PY springs and TZ spring, these are all basically for nonlinear interaction.
Yes, sir.
So these are the beams, the piles,
Yes, sir.
represented as beam, and those are the interaction model. Also, I showed one more model, I think, for the liquefaction analysis. So look at this system. This more detailed modeling approach is given. So these are the beams, right? And at the top, the entire system, like the generator, blades, those are all modeled as a lumped mass. It's just a simplicity. There's a simple model that we have used. And these are the lateral springs with dampers.
Yes.
And these are connected with the soil column. This is a soil column. So when we apply the seismic shaking at the base, the soil deformation will be applied on the end node of the outer node of the PY spring. So this is a very interesting way of modeling the entire system. So which you are looking at, the soil deformation will be applied directly on the spring, and the pile deformation will be again transferred to the soil through this PY spring only. So it's a basically the interdependent behavior can be modeled.
Yes, sir.
I
Sir, how
hope.
about continuum modeling, sir?
Yeah, you can go for continuum model, which will be most rigorous model, but it will be time consuming, expensive.
Sir, in that case, how can we consider the end boundary conditions, sir, in case of continuum modeling, sir?
Yeah, so in case of continuum model, the soil is modeled as a, see, this is a continuum based model. Look at this
Yes, sir.
model.
Yes, sir.
So the soil is modeled as a three-dimensional continuum, and
Yes,
piles
sir.
are embedded within the soil. Okay, so
Yes,
these are
sir.
the piles.
Yes,
These
sir.
pile nodes and the nearby soil, so those are basically connected with some interfacing elements.
Yes, sir.
So those interfacing elements are basically incorporated in the model to capture the soil structure interaction.
Yes, sir.
So that will transfer the load from pile to soil as well as from soil to pile.
Yes, sir. Sir, but at below, after your model, sir, below 90-meter depth, sir, we give fixity at the base.
Yes.
But what about the end boundaries? That is after 150 meters, should we consider fixed there or should we give hinged modeling, sir, somewhere there?
Normally we fix the model, But if
Yes,
we
sir.
apply earthquake loading, you have to release the
Yes.
fixing. You have to
Okay, sir.
release.
Can we consider free field modeling to the
Yeah,
surroundings
yeah,
and only
correct, correct. So what you are saying is absolutely correct. So for seismic loading, we need to apply free field boundary condition. So
yes,
different software has different type of analysis module. So
yes, sir.
at the outer boundaries, you can
Yes,
assign those free field boundaries.
yes,
So
sir.
which will follow the seismic motion.
Yes, sir.
Boundary conditions are such. If you
Okay,
apply
sir.
the seismic shaking, it will follow the free field boundary condition.
Yes, sir.
Yeah.
Thank you, sir.
Also, you need to ensure the wave reflection, so it should be minimized. Any kind of wave
Okay, sir.
reflection from the outer boundaries.
Okay, sir.
Okay. Any other question?
There are few questions in the chat session. The first question, do we consider the lateral load that acts on the pile because the tides while
Krishna,
designing? Hello?
let them ask.
No, he's not. They are not
Otherwise,
on.
I will leave. Is he present now? Whose question is this? Please unmute
Mr.
your
Mukund.
microphone.
Mr. Mukund, are you there? Mr. Mukund Chogali.
And then it's just like, so you leave it. So, are there anyone having doubt? Want to ask questions?
Good evening, sir. Hello.
Yes, yes. You are
Please,
audible.
please, we can hear
Amit
you.
Kumar.
Yes, yes. Sir, in case of helix pile, is it
Helical.
need to consider corrosion resistance reliability criteria?
Yeah. So basically, those piles are basically made, some anti-corrosion painting are generally done.
Actually, sir, in case of concrete, it is a surface is rough, but in case of steel, there is a smooth surface. So there is any frictional resistance?
Yes, definitely. So steel piles, are you aware of steel piles? Steel tubular piles like
Yes,
monopile?
yes,
So
yes,
helical piles are nothing but the steel tubular piles.
yes.
But the only difference is those helical plates are attached to that, those the shaft.
Okay. Okay. Thank you, sir.
Okay, so thank you. Thank you, all the participants. And sir, Sumanta sir, I have something to say for you.
Yeah.
Actually, we Shiju people, you never say no. Always yes. So we are very happy to get
Your
you
voice
here.
is breaking.
And without your shadow and wing, we cannot grow.
Internet connection.
Am I audible now? Hello?
Yes, yes.
Yeah,
Right
yeah,
now
yeah.
it's
Internet is. Okay. Sir, actually, when ever we see you people are in trouble or problem, we approach you, you never say no. You are so nice and so supportive and collaborative and cooperative. So we are very much happy, sir, to get you. And
Yeah. Thank you.
without your shadow and wing, we cannot grow, sir. So IT Bhubaneswar is like a castle for us, and you are
I
the
can.
king in there for us. So we love you, sir. We love you very much.
Yeah,
So that's all, sir. Actually, I thought since long I was thinking that I should say something for you. We are happy, sir. Our student is so happy. They went for their summer internship under you. They appreciated it so lot, so much. Miss KK from Uganda, our foreign international student, she was so
yeah.
happy doing your internship under you. So we are so happy,
Yeah,
sir, to get you.
yeah.
We
They
love you,
did
sir. We
very
love you,
good
sir.
work. Yeah,
Yes.
yeah. Thank
A,
you.
a, a great insight, sir, given by sir, a great insight, sir, towards the
Yes,
young
sir.
researchers, sir, in the field of
Uh,
foundation engineering as well as the collaboration, how structural engineer as well as
yeah.
geotechnical engineer can work together. Yes, great, sir.
So if anyone
Thank you
is
Very
so
happy,
having
much, sir,
sir.
any
for
doubt, they can send a mail. Okay, if
Uh,
any doubt or any question is still there, they can send a mail. I have shared my mail ID.
So could you share in the chat session?
Yeah, sure.
okay. So, sir, please don't stop to bless us. Don't stop to cooperate us, sir.
Yeah,
The way
definitely.
you are cooperating,
We have to
please
help.
keep doing, sir. Thank you, sir. So let us say good night.
Yeah,
And
good.
in the